Okay, let's start. So I think it might be good to discuss what you guys are doing with each other, not necessarily only on Discord, but in person as well. So today we're going to discuss this Banach Contraction Principle. Like I said, it's not as sophisticated of a thing, but still it has a lot of different ideas that are sort of like the starting point. We already applied this to the context of iterated function systems and generating fractals and stuff like that. But last week we took this as a black box. So now we're going to sort of discuss this, and we're going to unfold the proof and understand the proof itself, and realize sort of certain ways in which you can, in fact, approximate certain sets. This, in fact, gives you a certain approximation scheme as well. We're going to discuss all that. So this is the situation. If I have a complete metric space, and from the first part of the class, we know by now that the moment you see the word complete, that means that in the proof somewhere there should be a Cauchy sequence. Okay? Because I want to say, oh, this sequence is Cauchy. Because the space is complete, it has to converge to some point, right? That you should immediately think of that. And I have a function defined on X, sending it back to itself. So it's a dynamical system. And if this dynamical system is, it's a contraction, that is to say, the Lipschitz constant is less than 1, then there's a unique point, X star, in X, such that this singleton set is the set of fixed points. That is to say, this is the only fixed point, and it's also the only periodic point. Now, this is very useful in different areas of math. You sort of like use it because it gives you a unique fixed point. And typically, when you want to find a unique something in a certain situation, for instance, in the context of differential equations and stuff, well, sometimes you can apply this. That sort of requires finding a nice complete metric space and finding a nice contraction on that space and so on. But from a dynamical point of view, this really says that the dynamics of a contraction is trivial. It's not, there is not much interesting stuff going on. Okay. Now, let's think about this. So for instance, if you were to have on the interval, the doubling map, clearly this is not a contraction. F of x equals 2x mod 1. And the graph looks like this. Are we all clear that this is not a contraction? Right, because take 2 points and look at the distance between them. Well, the moment you start iterating, their distances are going to keep expanding by a factor of 2, in fact. And indeed, in this case, we have fixed points, we have periodic points, and this is sort of like the opposite situation, as you can imagine. So the number of fixed points of time n, so the n periodic points, is like 2 to the n or something. Let's just say proportional to 2 to the n. Okay, so this is, as you can see, dynamically very different. From a dynamical point of view, a map like this, even though it looks very, very straightforward, very simple, it's a single variable function and so on, this is sort of like the dynamically interesting example compared to this. Okay. Now let's even before going into the proof of this, let's start to understand this parameter here a little bit. So what happens if I were to say, oh, maybe my function is not a contraction, but Lipschitz constant is less than or equal to 1. So in this case, can I say anything about, what can I say about the fixed points or periodic points for my transformation? Can I say that it has a unique fixed point?
Like in cases, if it's less than the but it's equal to 1, I don't think it guarantees 1.
Yeah, so for instance, you can say, I can take the reals, right? So I'm sort of imagining this is sort of like my playground. Well, if I were to take the identity transformation, clearly, it's an isometry. In particular, the Lipschitz constant satisfies this. Any point is a fixed point, okay? But on the other hand, let's say G, if I were to do this, translation by 1, you see this too is an isometry. After all, I'm just shifting the line to the right by 1 unit. This has no fixed points, okay? So this doesn't quite work, okay? Are we clear about this? Okay, so you really need, for this contraction principle, this expression. Actually, we can generalize this, but let's leave it like this. How about saying this? So in the Lipschitz property, we have this less than or equal to, right? So let's write it like this. So this is C times P of x comma y. So what if I were to look at this expression? So this certainly contracts the distances, but I don't have a number less than 1 here. This is also something that you may want to look into. Any guesses as to whether or not this has a unique fixed point or many fixed points? Yes? Well, it depends again, okay? So look at this. I'm going to have a function defined on the complete metric space of real numbers that is not less than 1. And let my function to be x plus 1 over x. This has no fixed points, it turns out. So the exercise is to verify. On the other hand, if you have a function f, you have a dynamical system f, on a compact metric space, then this property does guarantee that you have a unique fixed point. Compact metric. And f satisfies strict inequality, like so, then f has a unique fixed point. Which is also the unique periodic point and blah, blah, blah. Let me not write it. It's a very nice exercise. Okay. Any questions about these?
I do have.
Yes.
So maybe it's just to have the same purpose as completeness does, but I'm curious as to why the exercise is talking about compactness rather than just completeness. Do we also need like the total boundedness as part of that exercise?
Ultimately, yeah.
Okay.
I mean, so would you agree that this has no fixed points? Because I'm saying f of x has to be equal to x, which means that this has to be 0. But for x bounded from below by 1, this never can be 0. Okay, so somehow.
Well, when I consider the domain to be
No, no. You always need completeness.
Right.
Compact
So
metric
the
spaces.
reason it fails, I guess, yeah, that's what my confusion is. Isn't the reason that one fails, couldn't it be just boiled down to completeness itself?
No, this is a complete metric space.
That's complete.
Yes. Yes. Okay, that's an exercise. Okay, so that's part of the exercise, that this indeed is complete. It's essentially the same proof as showing that the reals is complete.
Isn't that also bounded though?
Say again?
Like from 1 to infinity, isn't that bounded?
It's not, it's bounded from below, it's not a bounded subset.
Oh, I'm thinking of closed subset.
Yes, yes, yes. Okay. Because this is so useful in different areas, people sort of like have been thinking about different variations of this. Okay, but just wanted to mention these. Okay, any questions about these so far? So let's now discuss the proof. So I'm going to divide it into a couple different pieces. First, I want to show uniqueness. Okay, there's a saying that uniqueness is a specific case of existence. So unique means that you look at the set of the things that you want, and that set has to have at most one point in it. Okay, so first we're going to show it has at most one point, and then we're going to show it has at least one point. So the only number that is less than or equal to 1 and greater than or equal to 1 simultaneously is 1. So that's going to be the proof. And after that, we're going to sort of look back into the proof and extract certain estimates. And that's going to lead to what Barnsley calls the collage theorem. Okay. Now you see, something can be unique without existing, at least in mathematics. So first we're going to do uniqueness. By the way, let me just abbreviate by L, the Lipschitz constant, because it gets cumbersome to keep writing this. It's a number less than 1, by assumption. Now, first claim is that if I have 2 fixed points, they have to be the same point indeed. So one way of doing this is to take 2 points. Let me say x star and x dagger in the fixed point set. I want to show that these 2 points are in fact at the same point. Okay. Well, we're going to have to use the property of the properties of the metric. So one thing I can do is to show that their distance is 0, and that's what I'm going to try to do. Okay. Now x star is a fixed point of f, which means that I can replace x star by f of x star, and likewise x dagger. But then f is Lipschitz with L as a constant, which means that this is bounded from above by L times d of x star comma x dagger. Now this number is a number that is strictly less than 1, which means that this number is strictly less than this. Unless these two are in fact the same point, in which case this would be 0. But then again, maybe I should write it like this. Say they are not the same. Not the same thing as this. Okay? So I have some number that is positive, and I'm saying that number is strictly greater than itself. There's no such number. Okay? Contradiction, which means that they have to be the same point. Questions about this? Okay, it's a silly game, of course, but that's how you do math. Okay, now next I want to show, in fact, that the set of periodic points of f is the same thing as the set of fixed points. Now recall that the set of periodic points of f is the union of the sets of fixed points of any iterate. By definition, per of f is the union of all fixed points, of all iterates. In particular, certainly fixed points of f is inside here. Okay? Which means that in order to show this equality, I need to take a periodic point of f and then show that, in fact, it is a fixed point. Okay, so let me let x or x star be a periodic point of f. Maybe I should write it like this. P be a number such that f to the p of x star is x star. So x star, I'm saying, is a periodic point. I want to show that, in fact, in one time, x star returns itself. So let's try this. I don't remember now, but okay. So I want to bound this by some number that decays. If I can do that, they're going to be the same point. Well, let's do this. So instead of there are usually multiple ways of proving these. Let's try this first. So let me replace x star by f to the p of x star. Oh, okay. Let me replace this by f to the p of x star as well, so that I have, in the second entry, f to the p plus 1 of x star. Now, taking out p copies of f is going to give me an upper bound of this, of the form L to the p of d of x star comma f of x star. You can also imagine that I'm here using the fact that the Lipschitz constant is submultiplicative. Well, okay, L to the p is some number less than 1. Okay, you see the same point, same argument, basically. Say they're not the same point, which means that this is a positive number, and then this is bounded by this. Then there is no positive number that is strictly less than itself. Okay. Which means that, in fact, f of x star has to be x star. Okay. Any questions about these so far? So I'm not saying at this stage that f indeed has a fixed point, but at the very least I'm saying that if it has a fixed point, it has to be unique, and it also has to be the unique periodic point. That's what we have. Okay? So now we need to produce that fixed point. Well, let me just start with some initial condition, and let me look at its iterates. I'm going to start with some point x. So I guess in the statement of the theorem, I should say that let x be a non-empty complete metric space, but of course metric spaces, it's better to think of them as non-empty sets, otherwise there is nothing to do. There's a unique function defined on an empty set and everything. So this is now with the uniqueness, existence. Let x be an x. I take an arbitrary point and consider the sequence. Let's write it x bullet defined by x sub n equals f to the n of x. Okay? The claim is that this sequence is Cauchy. Once it is Cauchy, because I assume that x is complete, it's going to have a unique fixed. It's going to have a unique limit. Okay. Before, instead of dealing with these epsilons and deltas, I'm going to start with the expression that I'm trying to bound, which is the distance between the nth term of the sequence and n plus pth term of the sequence. And then I'm going to try to see how I can do this. Okay? I'm going to continue over here. So I want to bound this expression. The position of my initial condition at time n and its position at time n plus p. Any guesses as to how I can bound this by something that decays? Yeah.
L to the n. Well, L to the n times
Something, but how do you get that?
F of p.
How do you get that?
From lip f is less than 1.
But okay, but
Similar logic is from the uniqueness proof right over there.
that's okay. But then, so you're saying this. Okay. But you want to bound it by something that decays in n, but that does not depend on p. How are you going to get rid of this p?
Will decay to 0
How do you know?
because it's less than 1.
What is?
L is less than 1, so L to the n is less than L.
I understand, but for any p that has to hold, you want to bound this by an expression, right? Because in the definition of Cauchiness, you want to have some bound. So, you want to say there's some n, capital N, such that for any lowercase n after uppercase n, and for any p. So you want to be able to say, no matter how further I go in time, I'm going to have the bound. So this has to be bounded. So you want to bound it by something that doesn't depend on p. It's going to depend on n. And you're right that it does decay in n, but you want to get rid of this expression.
Right.
Any guesses as to how to get rid of this p? We actually used this trick a couple times already in this class.
Are we going to use some sort of telescoping?
Exactly, right? Yeah. You can write it like this here as well, but let me just do this. Well, the point is that if you want to compare the position at time n and n plus p, well, instead of doing that comparison in one step, you can compare consecutive times. So compare n to n plus 1, n plus 1 to n plus 2, and so on. And then you'll be able to use this Lipschitz property for each of those estimates. And then finally, I have d of, let me write it here, f to the n plus p minus 1 of x, comma, f of n plus p of x. Now, to each of these, I can apply the Lipschitz property, and these are going to give me some bounds. So from this, I'm going to have L to the n. From here, I'm going to have L to the n plus 1. From here, I'm going to have L to the n plus p minus 1. And then I'm going to have a factor. Okay? I just did what your colleague suggested. And then, of course, the point now is that this is the tail of a geometric series that converges because L is less than 1. Okay, so let's compute this. So I can factor out the L to the n. Then it is 1 plus L plus dot 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 plus L to the p minus 1. Okay. Do you remember the formula for this? We had discussed the formula. You can, let me just derive it again. So start with this, and then you multiply it by 1 minus L. So this gives you a copy of this minus a copy with the exponents 1 added. So this comes from this minus L times 1 minus L times L squared, L times L, and so on. So minus L squared, minus L to the p minus 1, and then at the end you're going to have minus L to the p. The middle terms cancel out, and you're left with 1 minus L to the p, but you've multiplied it by originally the expression 1 minus L, which means that this is exactly L to the n, and the middle term is 1 minus L to the p divided by 1 minus L. And then I have this factor. Questions about this? Now you see this trick is very useful. Now I can get rid of this p, you see? Because this is bounded from above by L to the n divided by 1 minus L. I can just drop this and it would increase possibly. So you see, this is an upper bound of this, for this, that depends on n, that decays exponentially fast with n, but that doesn't depend on p. Which means that this is indeed Cauchy. Okay. Now you can sort of like deal with, epsilons and deltas, but let me just leave it to you. So how would you do this perhaps? Maybe just discuss this a little bit. So what you want is this. You want this to be an epsilon. Okay, so fix an epsilon. Since this expression decays exponentially with n, you know that there is some capital N such that this expression is less than epsilon. And in fact, for any n, any lowercase n, after that uppercase n, it's going to be even lesser. Okay, and based on that, once you sort of like choose that n, it shows that it is Cauchy. Questions? Yes.
It's still a little bit unclear to me. Like, how do we know for sure that d of x comma f of x doesn't like counter the decreasing order of L to the n of O?
Because x is fixed.
Do we have to? I mean, it feels like we have to implicitly use the Lipschitz being less than 1.
No. At this stage, we use it. Once you fix x, this is a number. I'm not saying that this convergence happens uniformly in the initial condition. I'm not saying that. Which is an important point. You see, so we're going to discuss that in a second, but the point is that this estimate, and there are other estimates that are related to this, does say something about how fast you have the convergence. So obviously, if you started with a fixed point, you're already there. So the sequence converges in 0 step. But if you started somewhere else, it's going to take you some time. Still exponential, so it's good, but it's reasonable to expect that. For some other points, this convergence is going to be slightly slower. Okay. Any other questions about this? So x bullet is Cauchy. So this sequence of iterates of x under x is my initial condition under f, and x is complete, which means that it is a limit. So now, so x is complete. So there is an x star in x such that, let's just write it like this, limit as n goes to infinity of f to the n of x equals x star. Now we want to show that this indeed is a fixed point. Okay, at this point, I mean, perhaps it is obvious, but still. And again, I can use the same trick. I can look at the distance between these two guys. Then I'm going to bound it by some number that is very small, basically, right? So I can inject into this f to the n. Plus maybe I want to put f to the n plus 1 perhaps. Yeah, let's do that. X comma f of x star. So I use a triangular inequality. So I have here one copy of f, which means by the Lipschitz property, I can sort of take out that f and bound this by this. So this is let me just skip this. Of course, if I were to delete this L, it would increase. So let me just write it like so. D f to the n of x comma x star. Okay? But then I said that this sequence converges to this point, which means that there is some n such that after that n, this is bounded by epsilon over 2, and likewise this. So for any epsilon, this number is less than epsilon, which means that this number has to be 0 by the, what was it, the n epsilon of room principle. Okay, so that's the end of the proof. Found the fixed point. First I showed that there is at most 1, and I showed there's at least 1, which means that there is exactly 1. Questions about this? Yes?
From the second last inequality to the last inequality,
Yes.
the second term of each of those, are you using the Lipschitz condition and then taking out the F?
Yes. 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 Exactly. I mean, I didn't have to because, if this converges to 0, any number times that number also converges to 0. So it doesn't matter, of course, but yeah. So you see, now we can start talking about the estimates. This proof, when you really think about it, it says that no matter where you start initially, you start at a point, you keep iterating your dynamics, so things start moving, but any point exponentially gets closer and closer to that unique fixed point. So somehow the dynamics sort of like contracts the whole space into one point. Questions? Yes. So, it's not that sophisticated, as you see, compared to sort of like the completeness of the hyperspace, for instance. But still, it is very useful. Now let's talk about estimates that you can derive, basically using the same ideas in the proof. I'm not going to prove every single one of them. Estimates. In the context of the contraction principle. So the same assumptions. You see, this is important, having estimates, because typically, at least for the purposes of applications, this abstract generalities or abstract nonsense does give you that there's a unique fixed point, but it doesn't tell you what the fixed point is. But for application purposes, if you can get an approximately fixed point or some point that is approximately, near the fixed point, typically that is sufficient. So 3 estimates I'm going to write down, but I'm going to mess up, so I'm going to write it while looking at them. Okay. So first estimate. And this is also the basically collage theorem in the book. Okay. For any x initial condition in x, and for any non-negative number, I want to say something about the distance between the nth iterate of x and the fixed point. And it turns out that this is the estimate. It's a good estimate. So this is bounded by L to the n divided by 1 minus L times d of x comma f of x. Or maybe I should say that the collage theorem is the case when n equals 0. Okay. That's the first estimate. The second estimate, and L is the Lipschitz constant of f. The second estimate is this. So all of these are useful in different contexts. Again, for any x, and for any non-negative number. So I should also ask, perhaps, what is f to the 0 of x? It's just x, and it's x at time 0. That's what I mean. So now I have the n plus first iterate against the fixed point. This is bounded by L divided by 1 minus L. Where is this? Okay. The distance between the nth iterate and n plus first iterate. So you see, this sort of like gives you an upper bound in terms of how much you moved from by the end of time 0. But sometimes, maybe somehow you have some estimate as to how much you move between time n and n plus 1. So this is sort of like, you know, it's not as good perhaps of an estimate as this. And in fact, you can derive this using this. But still, this is useful. Third estimate, and there are many more, I'm sure, but these are the ones that I could think of and find. Okay, this is a third one. Again, I'm comparing the n plus first iterate to the fixed point. Yeah, and this is bounded by L times all this. Can keep writing actually, but these three are sort of straightforward. Most useful ones perhaps. Okay, now I'm not going to prove every single one of these. Let me just prove, well, this immediately comes from the, applying the Lipschitz constant and all that stuff. Because, you can replace x star by f of x star, and then you can pull out one time, and that gives you this, and so on. So that's going to be an exercise. This is an exercise. Let's verify that the estimate 1 holds. Okay, so I'm trying to bound this guy. Let me inject into this the n plus pth term. Okay, so we had already a bound for this. Let me just write it because I think I still remember. So what is this? It's basically that. This was what we proved just now in the proof. But then I had this term. Let me write it. Maybe I should write it like this. For any initial condition, so for fixed p, if I, oh wait, I should do it the other way around, sorry. So my n and x are fixed, because that's a statement. Fix x, fix n. P is not fixed, okay? if I keep increasing p, this term is going to, or this point is going to converge to this by the proof, which means that for any epsilon, there is some capital P, such that after capital P, this is bounded by epsilon. This is bounded by epsilon for any epsilon. So that this expression is bounded from above by this term plus epsilon for any epsilon. Take the infimums of all epsilons like that, and you get the expression. Okay. So maybe I should say once you take the infimum over this piece, this goes to 0, and you're bounded by this. Okay? Any questions about this? So now let me also write down the n equals 0 case of this collage theorem, so that you see that this is indeed what Barnsley discusses in the book. But the other exercises too, they're like nice. It's like you just like put things around. There are basically two tricks in this business. Either you sort of like inject some middle terms in there and get sort of like a geometric series, or you realize that x star is f of x star or something. And then you sort of like pull out a factor of L. That's basically the idea. If n is 0, this gives me something about the distance between the initial condition and the fixed point. Oh. So n is 0, that means that this is just 1. So this is nothing but d of x comma f of x. Okay, this equality or inequality specializes to this. Okay, so now, based on this, let's try to see how we can apply this to the context of iterated function systems through this Hutchinson theorem. Now, recall that last week we took this Banach contraction principle without the estimates, and we said, oh, this abstract thing does give you that there's a unique fixed point for the Hutchinson operator, which is the attractor of the B-IFS. But we didn't say anything about, what it is, or the inverse problem, so to speak. That is to say, and this is more applied in a sense, but still, it's very interesting. Let's say that you have a picture, you have something like a fractal in your mind, or you drew it somehow, but it's not explicit, nor is it, sharp. You don't have numbers and stuff like that. But you want to come up with a B-IFS that does generate that fractal that you have in your head. Okay? So the inverse problem. So let's say that you have a complete metric space. It's typically, R2, R3, and stuff like that. These are, reasonable spaces, but it applies in more generality. So fix I want a B-IFS that generates this. Find a B-IFS W, so a finite set of contractions acting on X, whose attractor, or whose, this Cantor set type of thing, is this A star. whose attractor is A star. Okay. So let me sort of introduce some notation. This is sort of like data fitting, if you want. Like I don't know the functions, and I have a set. And I want to find the functions that generates the set. So I want to find these such that A star equals the union of the images of A star under each of these maps. And of course, I'm not fixing capital N. If at all, if possible, I would want to keep n as small as possible, because that means that I get to sort of like compress the information of the set. Right? Because in week 1, in fact, in day 1, we described this Cantor set, and it was like it took this description, and I had to say, oh, you know, you take out this and blah, blah, blah. But then ultimately, if you can reverse engineer the iterated function system that generates it, all you need really is what? 4 numbers. 4 rational numbers, which means 8 integers. Okay, storing 8 integers is a lot easier than storing the whole description of the Cantor set, at least from a computational point of view, assuming the standard computational structure. Okay, and how did we apply this Banach contraction principle? Not to the original space, but to the hyperspace with the Hutchinson operator. Okay, so this is to say so this right-hand side is, you know, you abbreviate it like this, and this is, recall, the Hutchinson operator of this iterated function system. I don't know the iterated function system, which means that I don't know this function. Okay, now let's write this expression in that context. And then after that, we're going to take a break. So I want this. X star is A star. D is the Pompeo-Hausdorff distance. X is some compact subset that I start with. That's my initial condition. This is bounded by D of A, my initial set, and what happens to it if I apply the Hutchinson operator to it once. And this is again the Pompeo-Hausdorff distance, divided by 1 minus L. What is L? It's supposed to be the Lipschitz constant of this guy, but the Lipschitz constant of this guy is bounded from above by the max of the Lipschitz constants of these. So let me just perhaps write it like this. Lip of the Hutchinson operator. Okay? Any questions so far? I just translated this abstract formalism into the context of the Hutchinson operator. I didn't do anything. A is arbitrary. A is arbitrary. You see that pretty much everything is variable here. This is fixed. Someone gave it to you. They want you to come up with a B-IFS that generates it. So they want you to store it, okay? You can, or compress it. You can think of it like that. Which means that you want to come up with a nice initial condition and a B-IFS such that this happens. Well, this means that if you start with a set and sort of contracted versions of it that basically covers it. You can think of this as like that. That is to say, if you can make this, the distance, the Pompei-Hausdorff distance between the initial condition and the Hutchinson operator applied to it, small, then the set that you started with indeed is an approximation of the fractal that you started with. Okay? So find A and W, a B-IFS, such that this happens. And then at this stage, you really sort of start talking about specific examples, but let me just draw sort of like a picture. Okay, so I mean, in the textbook, there are very nice examples, but yeah, let's try doing this. I might mess this up. Let's say that this is your set, okay? That's your A star. This is your target. So you want to come up with a set and some contractions. That basically covers it. And one thing you can do perhaps is something like this. You take a circle. Let's say you take a box. Okay. And then maybe this is, let's say, the unit box. And you sort of cover the boundary like this. I mean, I didn't say that I'm going to come up with an example, but okay. You have like a bunch of these boxes, and each of these contractions does give you one element in your B-IFS, and this is your initial condition. Let's say that you end up sort of covering the whole thing. Maybe it's like this. How good you cover is basically this Pompei-Hausdorff distance, which we discussed before. You want to minimize that, basically. Of course, there's like a trade-off. The smaller this gets, the more complicated your B-IFS is going to get, probably. And the more the description of your set is going to get, probably. But that's sort of like what you do. Does this kind of make sense? I mean, it's clear that I'm not an applied mathematician, but this is what I got. What I understand they are doing. Okay. Questions? Okay, let's take a break, 5 minutes, and then we'll get back. Okay, I think we're all back. Let's continue. So here are some exercises which are basically variants of the Banach Contraction Principle, because typically, in this abstract generality, it's rather straightforward, but in practice, even if you're doing pure math, it's not clear what X is, or if your dynamical system F is a contraction that is defined globally, and blah, blah, blah. So people have different sort of versions of this. For instance, one version is this. I have a complete metric space, and in a point and a radius. And let's say that I have a function f defined on the closed ball in X, centered at x0 of radius r. Okay. At this stage, I'm not even saying that f is taking this ball into itself. But this is a metric space. It's a subspace after all. And this too is a metric space, and I can still talk about the notion of a contraction. If my function f is a contraction, and further, its Lipschitz constant is bounded by this guy, by this number, which is some number that depends only on the initial condition, the center and the radius, and of course the function, then the same conclusion as the Banach Contraction Principle holds. That is to say, f has a unique fixed point that is also the unique periodic point in this ball. And likewise, you can do the same thing with open balls. Okay. if I have an open ball and I have a contraction defined on it, such that the Lipschitz constant this time is strictly less than this bound, then the Banach contraction principle holds. Okay, these are nice exercises. Here's another exercise. Okay. Let's again start with a complete metric space and a function defined on it. If f is what some people call eventually contracting, so maybe f doesn't contract in one step, it contracts after some time. And the definition is the following, i.e., so I want something like this. There is a number c and an integer n such that for any lowercase n after this time, oh, there's some c and, of course, some other number, lambda. Yeah, let's write it like that. And for any x and y in x, the following happens. The distance between the nth iterates of x and y are bounded by some term that decays. This is bounded by c times e to the minus lambda n times d of x comma y, then the same conclusion as the Banach contraction principle holds. Let me just say MDCP. Okay. So this is sort of extending Banach contraction principle along the lines of dynamics. Like from a dynamical point of view, something like this is more reasonable of an assumption. Because you don't want to, because from a dynamical point of view, Banach contraction principle and other things is not really about this one transformation. It's about the dynamical system, or monoid generated by it. So here's an example. I'm going to define a function on the interval that is not going to be contracting, for instance. Okay. In fact, let me just do this here, so that we can discuss a little bit about these cobweb diagrams as well. Some of you started sort of discovering these ideas, but maybe I should ask, how many of you have seen or have heard of the name cobweb diagram? Okay, yeah. So this is sort of one method that you can use to understand from a geometric point of view how dynamics operate, at least in low dimensions. Okay, so I'm going to give this example. F is going to be a homeomorphism, maybe I should write it like that, of the interval. So it's the continuous map from the interval to itself. It has an inverse. The inverse too is continuous. And I'm not going to write the formula for it. I'm just going to draw it, draw its graph. Something like this. Now, these are two line segments. If you want it, I could, you can sort of like write the coordinates of this point, which is called the control point. And based on that, you can write sort of like an explicit piecewise expression for f. Not going to do it. In fact, let me change this a little bit. Okay. Change this just a little bit. And in fact, I'm not going to use a homeomorphism. Changed it. So I'm going to start here. But you should think of it like this. This height, let's say let's call it epsilon. If this is epsilon, I want this height, the control point, the distance, the vertical distance from the control point to the diagonal to be 2 epsilon or something. So that this has positive slope on this side, or slope larger than 1. This is epsilon, this is 2 epsilon. Okay. Now this function is not contracting, but it again has a unique fixed point, which is this point. And based on the Banach Contraction Principle, even though it is not contracting, you want to say something like so if I were to start with any initial condition, ultimately it would converge to 1, which is true. But let's see how one can understand this using this cobweb diagrams. What you do is this. Perhaps I should draw it even larger actually, so that I can draw things. So, epsilon. And I want to have a point, let's say, here. And let's say this is my control point. Clearly, this distance is larger than this distance. Okay, that's what I want. It's even worse. Okay, you understand. This is my f. So you start with an initial condition, x. Let's say you started here. You want to understand its iterates, how they act. Of course, I can figure out what f of x is from this by doing the following. I can just draw a vertical line starting at x all the way until I hit the graph. Boom. Okay? And if I were to sort of direct this beam this way, I get f of x. Okay, so far? Now, we want to understand iterates. One thing you can do is to, understand what f squared is, come up with a formula, draw its graph, blah, blah, blah. But typically, the functions that we're dealing with in dynamics is they're not complicated, they're not easy to sort of compose or at least write sort of like closed formulas for. So you want to sort of like stay with this one picture. So what you can do is this. Instead of going to the left, from here you can draw a horizontal line to the main diagonal and then project everything down. That is to say, instead of going that way, go this way. Somewhere here, and then come down. Well, this is on the diagonal, which means that this is f of x. Now I can apply the same reasoning. Instead of sort of looking at this, I can say, oh, I'm not going to go here. I'm going to start at x, go vertically until I hit the graph of f, then go horizontally until I hit the diagonal. Then I go vertically again until I hit the graph of f. And of course, because this is f of x, this should be f squared of x. And again, instead of going that way, I can go back to the diagonal, come down, and that would be f squared. Now I hope you see the point. It's like you can keep iterating this idea. You can say, oh, instead of projecting the beam downwards, I'm going to keep going like this. Boom, 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 boom. Okay. So this is why this is called a cobweb diagram. If you have sort of like a different map, you might have sort of like loops like this and so on. The point is that at each step, you're either drawing a horizontal line or a vertical line. Okay? And you keep bouncing your light, even though this is not, this is not a bisector, of course, necessarily. But you're sort of doing this horizontal vertical business to understand, at least geometrically, visually, what is happening. Okay? Yes?
Backing up a little bit, I just kind of lost what lambda was in that.
Some number.
Just, it's a...
Any number.
Okay, cool.
Yeah,
Just
yeah.
wanted to make sure it wasn't like super relevant.
Yeah, no. It is, you can sort of like associate some meaning to it, but it's sort of, you can call it, maybe it's like the Lyapunov exponent, blah, 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 blah. But the point here is that this is some expression that decays in n, which is exponentially decaying. That's what I wanted. If I wanted, I could have said, oh, lambda is a number less than 1, and then I have here lambda to the n. It would be the same thing.
Okay.
But let's go back to this. Any questions about this? Now, you see, this transformation is not a contraction, because initially you start here. If you were to take 2 points here, well, the distance between them is going to increase because the slope is more than 1. But it is eventually contracting. It has that property. Because no matter where you start with, eventually, if you start here in this box, your transformation is going to eject your point to this piece, where it is indeed a contraction. And indeed, you have a unique fixed point. So this is a case where this exercise sort of comes into play. Any questions about this? Okay. A couple minutes. There are more variations that are perhaps related to remetrizations and stuff like that, and that are also very interesting, but I don't want to sort of like complicate this even further. There's also what is called continuous dependence on parameters, or initial on the continuous dependence on the dynamical system, which is this, that we can start with a family of contractions. Each of them has a fixed point, and under certain circumstances, the fixed point of your dynamical system depends continuously on the dynamical system. So you want to imagine something like, oh, you're perturbing your dynamical system that you started with. That is also applicable, and Barnsley goes into detail about this. I don't think I have time to discuss that too much, but you're more than welcome to study this for one of your reports. It's a very nice sort of result. But at this stage, I think this much detail about Banach Contraction Principle is, I think, sufficient. Any questions about these? Okay, so with this, we're basically done with introducing iterated function systems, and on Thursday we're really going to start talking about more dynamics, what is called topological dynamics and symbolic dynamics, and how attractors of iterated function systems come with somehow a certain dynamical system, okay, which is essentially this shift transformation that we perhaps discussed a little bit. Okay, good. Thank you. I'll see you on Thursday. Okay. I think we should start. Hello. Good afternoon. So we're switching over to dynamics proper now. I mean, sorry, we're always like switching more and more into dynamics, but in a sense, we've always already been doing dynamics. So it's kind of bizarre. Before we switch over to what is called the symbolic dynamics, I wanted to give you this example. I think I promised you to give an example where you use this idea of this condensation or Hutchinson operator with condensation or B-IFS with condensation. And this is an example that's in the book. I just reappropriated to something slightly different. So you know, like when you're driving, let's say, and on the side of the road, there's a bunch of like poles, and they're like connected with wires and stuff like that. And so you want to sort of like generate at least that part of the image. Imagine sort of like a picture. And of course, there are like different versions of this B-IFS idea. Maybe you may want to use something called a local IFS, which is, you know, a bunch of IFSs that act on different parts of the image that you're trying to model. So for now, we're just trying to figure out one way to model this this picture of the poles on the side of the road. And so this is sort of like the side of the road. So let's start with this, okay? I'm going to have one pole like this. I'm simplifying the picture, of course. Let's say this is one pole. And let's draw some wires like this. Now, I'm not connecting the wires to the next pole, okay? Now that's, so what I drew in red is a compact subset of the plane. So my X now, the complete metric space that I'm going to use is R2. And let's call this, let's call it L. L is going to be the condensation set. And so this is a fixed point in the hyperspace, condensation set. Okay. Now I want to turn this into an IFS. Okay, so I need a contraction. I wrote the formula here based on the picture I drew in my notes, but something like that should work. You can play around with the parameters as well, but let me write it here. I'm going to have only one contraction. And it acts like this, okay? I'm going to feed to it a point in the plane, x comma y, and it's going to give me back. So I want to basically have this image, but duplicate it here, okay? So that means that I need to shrink it by some factor, and the one that I chose here is 5/9. But then I want to shift it to the side, right? I want to move it this way and this way. And I can do this by, for instance, plus 4/9 in the x-coordinate, and then plus 2/9 in the y-coordinate. Now, I'm not exactly claiming that these numbers are going to work, because ultimately I'm going to keep running this, Hutchinson operator. But even though I'm sort of trying to create the illusion of this horizon, I'm not allowed to go to infinity in the plane. So this length has to converge to zero length in finite distance, okay? Because otherwise it will not be compact. So maybe these numbers are kind of iffy, but you can certainly play around with them, okay? Now, so this is my condensation. This is one contraction. I can take it and put it into a capital W. Let me continue here. So my Hutchinson operator associated to this B-IFS, and certainly it is a B-IFS because it's a contraction, with condensation L acts on this space like so, right? So you feed to it some compact subset, take that subset, apply W1 to it, and then take the union of that set with L. So L union this. Okay. Now this is this is fine. It's a contraction. It's a Hutchinson operator with condensation, which means that Banach Contraction Principle, all that stuff, gives you that there's a unique fixed point of the Hutchinson operator with condensation in this set. So in this space, which means that you have a unique A star, which satisfies this condition. Okay. Now, this limit set certainly contains this condensation, but it contains also all of its images under this contraction, which means that if it contains this, certainly it has to contain the same picture here, like this, and so on. And if it contains this part, it has to contain its iterate under W1 and so on. And as you see, ultimately you get the whole picture like this. And indeed, let me just write it here, it's getting more complicated. This limit set is nothing but L union with its iterate and a second iterate and then third iterate and so on. W1 squared and so on. Okay? So you see, I was able to, so is this sort of like clear what I'm trying to do here? So in a sense, I was able to sort of compress this whole sort of like vista into having only this picture and then repeating it. If I wanted, I could sort of like try sort of generating this using an IFS as well. But in a sense, having a condensation set or defining the condensation set as this first pattern turns out to be perhaps more useful or simpler. The math behind it is what we discussed before. But as you can see, when it comes to applications, like this is really opening up new vistas as to how one can use iterated function systems to generate things and so on. Questions about this? Okay, so now let's switch to symbolic dynamics or coding. And so here I gave a couple exercises that is somewhat related to this. So the basic idea is a very simple computational question, which is that you have the number square root of 2, and you want to compute some numbers, some digits of it. Okay, now there are a couple different ways of doing this. And so here are 3 different ways you can try using 3 different methods. So one of them is what is called the Newton's method. How many of you have seen Newton's method? Okay, most of you. If you don't know this, it's a beautiful thing, and it's like it generalizes later on to what is called the KAM method, short for Kolmogorov-Arnold-Moser method. So I would highly recommend that you learn how to do this. And Sternberg's notes literally starts with a discussion of this. So you can go ahead and study that and report it if you so prefer. Another method you can do is you can start with the function square root of x. Okay, so it is not differentiable, of course, at x equals 0 because its derivative is infinity. But 2 is larger than 0. It's away from 0. And away from 0, this is a beautiful function. It's perfectly fine. You can look at the Taylor expansion and so on. How many of you have seen Taylor expansions? And you start with a function, you keep differentiating and so on. You put that in a power series, and somehow that's like an approximation at the very least. And then the third method is through linear algebra, which is called this power method. How many of you have seen this power method? So this is about computing eigenvalues. So you have a linear operator, or a matrix, square matrix, and let's say that you have one eigenvalue larger than 1, and all the other ones are less than 1. The point is that to compute an eigenvector for that leading eigenvalue, what you can do is, in that situation, what you can do is you can start with any vector, and you can keep taking powers of the matrix. Ultimately, that vector should converge to some vector that is in the same direction as your eigendirection. That's sort of like an idea. This probably is going to be somewhat complicated because you need to come up with a matrix that is easy to iterate, such that one of its eigenvalues is root 2, and the other eigenvalue is less than root 2. So for instance, you could try using this. But with this power method is not going to work because the characteristic polynomial for this is lambda squared minus 2, which means that one of the eigenvalues is root 2, that's fine, but the other one is minus root 2. So you want other eigenvalue less strictly so that it decays under the power method. So this probably is not going to work. So you need to come up with some other thing. Okay, any questions about these so far? Okay, now I want to discuss a different way of computing digits of root 2. And in a sense, this is a lot more simpler. It's very basic. And this is basically related to the dynamics of the notion of this orders of magnitude. In other words, it's about the dynamics of 10x. Take a number, multiply it by 10. So let me just say. So the point here is that you want to identify, in a sense, where root 2 is relative to other things, other numbers. So one thing you can do is this, okay? So instead of looking at root 2, you can look at its square, okay? Certainly, 2 is strictly between 1 and 4, which means that root 2 is between 1 and 2, strictly. That is to say, in the real line, it's somewhere here. Okay, so now you want to do the same thing, but you want to sort of zoom in to this interval. If you were to zoom in, you get this. And in fact, let me say this is basically multiplying by 10. And so that this is 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So in order to find the position of this guy, what I can do is I can multiply everything by 10, zoom, then find the position of 10 times root 2. Okay? So where is this? Well, again, instead of looking at the square root, of course, the point is that the square roots are complicated. You take the square of this. The square of this is, what is it? It is 200. So what are the squares? You start at 100, you end up with 400. So somewhere there's like the largest number less than root 2 and smallest number greater than root 2. It turns out, I did this calculation, it turns out that 14 squared is 196 and 15 squared is 225. Okay? That means that this number is between these two. In other words, 10 root 2 is between 14 and 15. Okay, so that means that it is somewhere here. Well, if 10 times root 2 is somewhere between 14 and 15, that means that root 2 has to be somewhere between 1.4 and 1.5. Okay, so here, at the end of this step, I was able to see that the first digit has to be 1. Now I can also see that the second digit has to be 4. And I can keep going like this. It's going to get more and more complicated to take these squares and stuff like that, but in principle, this is sort of like a valid method of finding digits. Okay, any questions about this? Now the temporality in this dynamics is somewhat confusing because, as you see, in a sense, root 2 is where it is when we first started. It's just that we didn't know where it was. In a sense, we didn't know the address, is what Barnsley would say. But to figure out the address, we zoom, so apply our expanding dynamics, figure something out, and based on that thing that we discovered, we have a better understanding of where it was to begin with. So it goes backwards and forwards in a sense. Any questions about this? Okay. So now let's switch to something more dynamical, and we go back to Hadamard. He's typically considered to be the first person who used the notion, the idea of a symbolic dynamics to do something. Okay. So Hadamard was interested in understanding what we would now call, probably what was called at the time as well, understanding the dynamics of the geodesic flow on a surface of constant or surface of negative curvature. Of the geodesic flow Now, I'm not going to define most of these words, but the main idea you should think of is this. A surface of negative curvature is something like a lower dimensional version of this curved space-time business. And geodesic is basically the path a line would take. That is, a light would take. So somehow it's sort of like the path of least resistance in terms of light and blah, blah, blah. So this is something that people want to understand. Abstracting out, at some point he realized that the problem eventually turns into this. You have three dispersing obstacles, and you have light bouncing, okay? Or, we can think of it as like a billiard ball. These are like, and we're thinking of it as, no friction and perfectly elastic. You keep going, and when you're bouncing, let's say from here, and you go like this, you draw the tangent, and then you draw the bisector, and you leave like this, okay? His understanding, his idea was that, and so light is sort of like bouncing around. His idea was that the dynamics of the geodesic flow, when it's moving around or inside this, is mostly dependent on what happens, or so what is the sequence of the obstacles the light, one specific light, is hitting. Okay? So for instance, these are like perfectly circular, imagine. Certainly there is, for instance, one trajectory like this. If you can sort of like figure out the right exact angle, you can make it so that the light bounces off between these two for all time. You have to be very precise, of course, right? Because if you miss just a little bit, well, you're going to bounce off and you're going to go somewhere else. In a sense, this is sort of one of the fundamental examples of what is called chaos. So this is what you would say a chaotic system. Nowadays we have more specific adjectives for these kind of things, but this is sort of a good way to start. Another example would be a period 3. Before going into that, let me just say this. So when it comes to this particular sort of trajectory, so your initial condition was somewhere in the middle, let's say, and you figured out just the right direction so that when you shoot your billiard ball or light in that direction, from that point, you're going to have a periodic trajectory. Okay? And that periodic trajectory would be, well, you can denote it by AB, AB, AB. Okay? Let's use a different color. You can likewise try to come up with different angles so that you have a period 3 trajectory. Let's say that maybe it's somewhere like this. Something like this. Okay? Now this would be a period, so let's say like this. ABCA, I guess I wrote ACB. Hadamard's big theorem was that given any sequence like this, there's a trajectory of the billiard ball or the light whose hitting structure is exactly that sequence. Okay?
Would that be from any initial condition?
Say again?
Would that be from any initial condition?
I don't know. Probably. No.
Couldn't you put them all in a line, and then you can't have a 3 period?
Say again?
Couldn't you put like all 3 of them in a line, and then you couldn't have like a 3 period?
Oh, yeah, but I want this particular configuration. I'm not moving these around. These are fixed. When it comes to billiards, the positions of things become very important. Yeah. And the sizes too. It's like, but let me just write it. Theorem. Given any sequence of ABCs, there is a trajectory of the billiard ball whose pattern is that. So let's say given any sequence omega of ABCs, there is a trajectory of a billiard ball. Let's say there's a billiard ball trajectory. Whose pattern is omega. Now I've put the original paper by Hadamard under the resources. It's in French because he was French, but and also Civitanovich's and other people's book called Chaos Book. He's a physicist and he describes this from a physical point of view, and he does simulations and calculations. It's like a beautiful thing. It would be a great topic to study for one of the reports. Also, This book is also, it's in public domain, so it's under the resources. Okay, so this is like the starting point of symbolic dynamics. So you start with some complicated dynamics, and if you can figure out one way to code your system and to turn it into basically sequences in such a way that, in fact, what happens now, you see, that is that the dynamics here, let's say for this periodic orbit, is duplicated by the shift transformation here. We're going to discuss the shift dynamics in a second, but this is sort of the idea of a conjugacy or semi-conjugacy. You start with a complicated dynamics, you code your system, or you code your space in such a way that your dynamics turns into this simple shift. Now you can sort of, some people sort of study this idea of a coding and use symbolic dynamics to understand more complicated systems. And then there are some other people who are specializing in symbolic dynamics that sort of like look into the intricacies. I'm going to give some examples of these things, but this is the starting point. Any questions about this? The one problem is that this is not true, and it's obviously not true, which is because of the following. Not every sequence, because there is no sequence or there is no trajectory of the billiard ball whose corresponding sequence would have AA. Because if you hit A, you're not going to hit A the next time. You have to hit B or C. Okay? So, provided that no terms repeat, no symbol repeats. Okay. Now this week, or this class, we're going to focus more on the symbolic dynamics and build some intuition. And then next week, we're going to connect this idea of the symbolic dynamics to iterative function systems. Okay. Let me also say that the fact that you cannot use every single sequence, but you can only use certain sequences subject to a certain constraint really corresponds to this notion of a subshift that I hope to define today as well. In fact, this turns out to be a subshift of finite type is what we're going to say. So SFT, let me just write. Okay. Okay, I want to give some definitions now. So this really is, so the underlying idea is the idea of so-called conjugacy, or in other words, equivalence of dynamical systems. You can do this for more general monoids and group actions and all that stuff, but let's just look at iterates. Okay, I have two sets and two functions acting like this. I'm going to call them conjugate. If there is a bijection, let's call it phi, from x to y that conjugates these two actions. If there's a bijection such that phi composed with f is the same thing as g composed with phi. So if you want to draw sort of like a diagram, this is the diagram that you would draw this is the same thing as writing this. Okay. How many of you have seen something like this before? Maybe in linear algebra you saw something like this notion of a similarity, or two matrices being similar, spectral theorem, all that stuff. This is sort of basically the same idea. So you want to think of this phi as a coordinate change. Okay, in linear algebra, for instance, you say, if I have a symmetric matrix, then up to an orthogonal coordinate change, that symmetric matrix is actually diagonal. Okay, it's the same idea. The difference, though, is that I'm allowing the coordinate change to be more general than linear, and likewise the transformations. So let me write it like this. Phi is a coordinate change here. And another way of thinking about this is to say that phi is a passive transformation. Whereas f and g, the dynamics that we were conjugating, you want to think of them as active transformations. The space is actually changing under f. And this active and passive transformation, this idea, it's not a mathematical idea really. It's a sort of like a philosophical idea, if anything. So, and how many of you have seen this difference between passive and active transformations? We discussed this in linear algebra, but so given any transformation, you can think of it both passive and active. It's, in a sense, how we think of it. Right? So, for instance, one example that I learned from Terence Tao is that let's say that you're reading a book, a digital book on your laptop, and you're scrolling down. You can think of it two ways. Either the object in front of you is going up, and you're reading more and more, or the object stays the same, and you're going down. Okay? Now, these two, you can think of the same thing in two different ways. But these two sort of like turn out to be different design principles, and like when it comes to designing things and user interfaces and stuff like that, it turns out that how you're thinking about the user experience is important, and here too. What is important, perhaps from a mathematical point of view, is that in this example, so what is the active transformation? The active transformation is you're doing something, which is you take this, move it upwards. Okay? The passive transformation is you don't do anything, you move yourself. Okay? So active goes this way, passive goes that way. So they're sort of like opposite. They do the opposite things in a sense, but ultimately they are the same thing. Okay. So this idea of a conjugacy is the notion of equivalence for dynamical systems. There are other notions of equivalence for dynamical systems, but this is sort of like the standard one, the most basic one. And when it comes to understanding dynamical systems from a mathematical point of view, of course it's a Western science, we're really talking about the taxonomy. So you want to classify it. When you're trying to classify a certain class of objects, you have to have a notion of equivalence. Okay, so you want to classify dynamical systems up to conjugacy. Okay. So here are some basic ideas. So the typical question is, I have two dynamical systems. Are they the same? Are they conjugate? And I'm going to give examples, but let me just say that this question ultimately leads to what is called the invariant theory. So you want to come up with certain things, certain numbers perhaps, or sets or whatever, that are invariant under conjugacies. Okay? Oh, maybe I should add one more definition here. Here I didn't assume that x and y are metric spaces, f and g are continuous and stuff like that. But if x and y are metric spaces, and phi is a homeomorphism from x to y, it's called a topological conjugacy. Okay? And is a homeo topologically. And more generally, if let's say x and y are vector spaces, or the reals, and phi turns out to be an affine automorphism like we discussed, then you call them affine conjugate and so on. So you want to make this conjugacy as strong as possible, because the stronger the conjugacy, the more properties are going to be preserved. But for abstract conjugacies, we already have some things. So if, let me just write it like this. So if you have a conjugacy from f to g, well, you know that their sets of fixed points have to be conjugated, and likewise sets of periodic points and so on. So if I were to take a point that is fixed under f and apply my change of coordinates transformation, I should get back a fixed point of g. Likewise for periodic points. Furthermore, for instance, the zeta functions are the same. Because if phi gives you a bijection between, fixed points and so on, that means that the zeta functions have to be the same. There are many other. If your conjugacy is a topological conjugacy, there are other things. There are things like topological entropy and so on that we haven't discussed yet, and probably we're not going to discuss at least in full detail, but there are other things. Invariants. You're trying to come up with invariants that sort of detect when two things are conjugate. The problem with stuff like this, invariant theory, is that often this goes only one way. Okay? So that just because you have, oh, this is equal, blah, 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 you're not necessarily guaranteed that it's actually a conjugacy. Okay, that's the main problem. Any questions about these so far? Okay. So let's do a simple example, more concrete. So some of you have started looking into the Mandelbrot set and stuff. Let's look at these two transformations. Let's say Z. You can, assume that these are acting on the complex plane or the Riemann sphere, as some of you have started looking into, or, as formal sort of polynomials. But let's say that I start with a polynomial like this. And let me have, maybe I should use a different letter here because typically people I'm going to use D here. Let me have another dynamics, which is this quadratic family. Is it plus or minus C? I think it's plus. It doesn't matter, of course, but. So this is what is called the quadratic family. For each C value, you have one dynamical system. And as you're varying C, you want to see, for instance, how the behavior changes. And this leads to this idea of the Mandelbrot set, okay? Which some of you already know. The claim is that these two are conjugates, okay? And so let me also say what is sort of like the purpose of looking at something like F. You might think of F as a generalization of what is called the logistic transformation or logistic family. So if Q, let's say L sub mu of Z is mu times Z, Z minus 1. How many of you have seen something like this? I know you saw it because we did it in differential equations. So in differential equations, you can see the continuous version of this. Basically, this sort of like models. It's a very fundamental. It's a very basic model of population growth. And so this mu, you want to keep it as a parameter because it says something about the initial growth rate. So you want to keep it as a parameter, and you want to sort of like move it around and stuff. And as you see, this is like a special cases of this. You can sort of expand it, and like you might as well just look at this more general thing. So maybe I should write. This is the logistic family, and this is the quadratic family. Okay. Now, for different values of mu, it turns out that the behavior of L sub mu is very different in terms of dynamics. And this leads to very interesting stuff like, Feigenbaum universality or period doubling, period bifurcation, a bunch of different things, which you might as well read in Sternberg's notes as well. But leaving that aside, the example is that these two are conjugate for some C. So I start with some arbitrary polynomial of degree 2, which ABD, let's say arbitrary complex numbers. Let's say A is not 0, so that it's actually degree 2. And I want to say that it is conjugate to this guy. In this case, it turns out that you can sort of like actually start writing it and find something, find a conjugacy. So claim there's a phi of the form AZ plus B, so it's an affine conjugacy. It's even stronger than topological, such that phi conjugates F to Q sub C, which means that to understand the dynamics of degree 2 polynomials, which means that from a dynamical point of view, remember, we're going to keep iterating this, so it's going to get complicated. All you need to, so you can just specialize to this one specific example, which is beneficial because in a sense, this is much easier to handle. And this too already is very complicated, as some of you know. Just one so you decrease the number of parameters from 3 to 1 by doing a change of coordinates. Okay. So how do you verify the claim? Well, you plug everything in, open things up, and try to solve it. Now, in general, things aren't as easy as this, but and depending on the type of dynamics that you're trying to sort of compare, you have different methods to show, to construct the conjugacy or to show the existence of a conjugacy. Which, in certain circumstances, you can actually use the Banach Contraction Principle to show that a phi exists, but it gets complicated. Okay, so I'm just going to take this expression and open it up. Okay, so the left-hand side is this. So let's open first this. So this is A times, and A and B are numbers here that I'm going to determine. Okay. a very important method in dynamics is to just assume that something's going to work, go through everything, and then sort of look back and see if things actually make sense. So, okay. So now I need to replace this with that guy. This is just basic algebra, of course. Nothing sophisticated happening here. And then let's consolidate. So that's the left-hand side of the equation. The right-hand side of the equation is G composed with phi. So what is this? This I can open, oh, I guess this should be Q. So this is this squared plus C. And then opening this up, I have AZ plus B squared plus C. Opening this up, I have A squared 2AB times Z, and then plus B squared plus C. So I want these two expressions to be the same. I forgot the Z squared here. Well, two polynomials are the same if the corresponding coefficients are the same. So that gives me a bunch of equations. So from the first numbers, I get, let me just write all of them actually here. So these are the numbers coming from here. And these should be equal to A squared 2AB, and then B squared plus C. Now these are, of course, nonlinear equations, but still, they're not complicated. Can I just leave this to you to solve? Or should I finish it? Okay, that's an exercise. Finish. Solve for A, B, lowercase c. So here the point is that lowercase a, lowercase b, and lowercase d was given to you, and then you came up with a conjugacy, and that gave you a coordinate change to some quadratic function. C is going to be determined based on lowercase a, lowercase b, and lowercase d. Okay? So in a sense, to understand the dynamics of these guys, all you can do, or one of the things you can do, is to simplify your problem to understanding this. Once you understand this, you can go back, because you have, so the difference is only a coordinate change. Okay? So as you see, this idea is very strong. It's a very powerful idea. Any questions about this? Yes?
Where'd the intuition come in for this b of z to be equal to az plus b?
Okay, yeah, okay.
Because, I mean, it works out very nicely over here, but I just don't totally get the connection.
There are a couple of intuitions. One intuition is that so one intuition is this, right? So you can think of any parabola as a graph transform of one of the standard parabolas. It's like, I don't know, maybe x minus 1 squared is really x squared shifted to the right. And then you can expand it like this and so on. And so what are those graph transforms? Those graph transforms are really affine transforms. That's one intuition. Second intuition is this. You say, okay, I'm starting with these two guys, and I'm trying to come up with a phi that is the best, that's as good as possible. So what that corresponds to from a computational point of view is to say that, you assume that phi has as many derivatives as possible, and you say, I'm going to open up the Taylor expansion, and I'm going to compare the Taylor polynomials, basically. So you want to conjugate up to 0th order. then up to first order, up to second order, and so on. This gets iffy to sort of like formalize exactly, but that's sort of like one of the ideas. So instead of trying to come up with a solution to this, you can differentiate it, assuming phi is differentiable, in which case things are going to get simplified, because instead of second degree, now you're going to have first degree and so on. Not quite, because you have compositions. Because of the product rule, it's going to be complicated, but still, you can try pushing it that way. And then you sort of like go back, and then you realize, oh, in this case, my Taylor polynomial doesn't need, it becomes 0 after 2 steps. So after all, this is the phi of 0, and this is phi prime of 0. We can do it that way too.
Interesting.
Yes. Dynamics is all about, it's like a, it's like MMA. You can do, there are so many tricks you can use. Is this sort of answering your question?
Somewhat. I think I need to simmer on it for a little bit.
Yeah, imagine sort of like the standard differential equations class, how you have like 5 different tricks and stuff. Like dynamics in general is like, that in steroids. And you also have to justify it and so on. But apart from that, yeah. Okay, any other questions? Let's take a break, and then when we come back, we're going to continue. Okay, let's continue. Welcome back. So let's now focus on dynamics on shift spaces. We defined this in week 1, and then we basically left it alone. This is a metric space. We have a certain metric, and on the notes, I wrote a couple of other metrics on it as well, and like compare them, which ones are Lipschitz equivalent, which ones are Hölder equivalent, blah, blah, blah. But what is more important at this stage is the shift transformation, okay? And so this is acting on the space of sequences. So my alphabet is m symbols from 0 to m minus 1. It doesn't really matter if you're using letters or integers, whatever. What matters though is that it's a finite set, and I'm looking at the set of all sequences, one-sided sequences, only goes to positive infinity to the future, let's say, taking values in A. And the shift transformation basically moves forward the ticker tape. Recall that we denoted, or one of the ways we represented elements in the shift space were these ticker tapes. And this is the 0th coordinate, 1st coordinate, 2nd coordinate, and so on. In a sense, these are sort of infinite dimensional vectors. And the shift transformation does this simple thing. Takes this ticker tape, moves it that way, and cuts the first piece, okay? So now the first piece is this, and so on. It's a very simple dynamical system. What are its fixed points? Or maybe I should ask, how many fixed points are there under the shift? One sequence, okay, so one of these, one point in this space contains infinitely many numbers. But I want a string of numbers that is fixed under shift.
Just infinite ones, or I guess for each of the elements of our alphabet, it being the whole
sequence. Okay, all of these. So in total there are how many? M. Oh, m minus 1, m minus 1. How many periodic points of order 2 are there, or period 2 are there? Yeah, so these are like fixed points, and so the point is that either it's going to be so you have like m choices for this, and then m many choices for this, so m squared. Okay. So let me just say the numbers of this is m squared. It should be the other way around, sorry. 2 to the m. Because you have, yeah. No, wait, it's the other way around. I was right. Sorry. M squared. Okay. Okay, because I have m choices for the first guy and m choices for the second guy. If I want to look at period to, points that are not fixed, I would need to subtract these many. So let me introduce another notation. Per of sigma sub 2, that means that I want 2 to be the least period. So I need to take this and subtract the number of fixed points, which is m squared minus m. Okay? Any questions about this? And it keeps going like this, of course. Question? Yes?
Could you put a little bit more elaboration into how you got this set of fixed points here? Because I'm confused on that.
Yeah, for instance, if I were to start with this guy, so my ticker tape has only ones. That's a 0 coordinate. This is one element in the shift space. Now, if I were to apply the shift transformation to it, that corresponds to doing this, right? You get rid of this part. Now this is a 0 coordinate. It's literally the same thing. That's what it means for something to be fixed. Okay.
Okay, that makes sense.
So that's one. So let's do this.
Well, it's the same even though you're getting rid of one of them?
Say again?
It's the same even though you're getting rid of one of them?
Um,
I guess you're not necessarily getting rid
Well, I
of
mean, it's an infinite thing. So
I guess that's true.
yes. So 1, 2, 3, 1, 2, 3. I think that's a song, no? I see a. Okay. So this, I claim, is a period 3. I guess it doesn't matter. Let's do 1, 2, 2, actually. Goes 1, 2, 2, 1, 2, 2. I'm saying that this is a period 3 point. So if I were to apply the shift once, I get, let me just draw this. Oh, sorry. I start at omega. This is going to be sigma of omega. This is going to be sigma squared of omega. And this is going to be sigma cubed of omega. I claim that here I'm going to get back the original sequence. Okay, shifting this once, I get 2, 2, 1, 2, 2, 1, 2, 2, 1. Is this okay so far? I shifted all of them. I got rid of the first entry. Now it's gone. I start here. Now, applying the same thing to this, I get 2, 1, 2, 2, 1, 2, 2, 1. It goes on like this. And then if I were to do this once more, this is the same thing as omega. This is not omega, because the first entries are different. This is not omega, because again, the first entries are different. Does this make sense?
Yes.
Okay. Any questions about this? So let's perhaps write this as well. What is the number of fixed points of the nth iterate, or sorry, the nth iterate? Number of fixes of sigma to the n. How many points are there? If this is squared. Okay. Okay, we kind of saw a similar pattern before in the context of the doubling map. Okay, so in particular, the number of fixed points at time n match between these two things. Now, there was an exercise that I erased. It said that if you have a conjugacy, then fixed points have to be sent to fixed points. Now, that is not sufficient, but at least it's some evidence that they might be conjugate. And it turns out that they are. The doubling map is conjugate to shift on two symbols.
The doubling map for the sawtooth.
Recall that this was a map acting on the interval and it was nothing but f of x equals 2x mod 1. And its graph looked like this. So the claim is this is conjugate to shift on two symbols. So instead of, I need to choose here m equals what, 2. Maybe we should put this in a notation, sigma m. Okay. So now, how can I build something like this? So I want a function phi that solves this functional equation. Now we cannot just plug things in. I don't really have a sense of how this phi should look like. But any guesses as to how I can sort of come up with something? So here, what do I need? I need phi to be a function from the interval to the sequence space. Now, how do you start with a number and turn it into a sequence of numbers?
Can we map the value of each element of a harmonic series or harmonic sequence to its output through f?
What is the harmonic sequence?
Like 1/2, 1/3, 1/4. You can retrieve n elements.
Almost. It's not as complicated as that. It's much simpler. Yes.
Base 2, maybe?
So instead of decimal expansion, you can use base 2 expansion. That is to say, you can take a point x and write it in terms of powers of 1 over 2, I guess, or powers of 2. So let's write it like this: x sub n divided by 2 to the n. Okay? The coefficients of this power series is this map. So I think we should start with n equals 1 or something. It's not that important. What is important is that this is what you end up with. You can sort of figure around, mess around with the details a little bit. So this is a function, okay? There are certain problems with this. this is basically the idea, but do any of you see any problem with this? The one problem is that given x, this representation is not unique, because this is the same thing as 0.999 and so on. This is in base 10. If you wanted to do this in base 2, you would write it like this. So in base 2. So somehow you need to make a choice. Let's make the choice that whenever we have this issue, choose the representation that doesn't have infinitely many zeros. Okay, now it's a well-defined bijection. Any questions about this so far? Okay, but we still need that this conjugacy holds. Okay, now let's try to understand what this doubling map does here. If I were to start with a number, the doubling map just multiplies it by 2, gets rid of, the expansion to what is after to the left of the decimal point or the binary point or whatever after the dot. So under this, well, I'm going to multiply it by 2 and then mod it out by 1. So what's going to happen here? Times 2 divided by 2 to the n mod 1. This is going to be, we started with n equals 1. So now it's going to be like this. So let me perhaps write this more explicitly. I started with this. Xi's are either 0 or 1, because that's in binary expansion. When I multiply it by 2, now I get x1 plus x2 divided by 2 plus x3 divided by 4, and so on. But this number is larger than 1, which means that this goes away, and I'm left with this guy. Under the conjugacy, which I hope now this justifies that this indeed is a conjugacy, this is sent to the sequence x1, x2, x3, and so on, and the shift transformation takes this guy to where this guy should be taken under phi. Does this make sense? It's kind of magical, but it works. It really works. Modulo some issues like like choosing the right expansion and blah blah blah. This is what you want, and this is why this doubling map is very important. You see, this is the idea of coding. I started with this transformation, and I did something which is this like very natural thing to do. Look at the binary expansion of a number, and that turns it into merely shifting the entries. Okay, so this then leads to this idea of a Markov partition. Whenever you have, this is sort of like this general principle, whenever you have a dynamical system that is in this paradigm of hyperbolicity, which is this stretch and fold type of dynamics, there is a Markov partition typically, which is sort of like partition. It's about partitioning the space in a certain way that gives you a conjugacy to a shift. So what is that partition? In this case, the partition is this is the first part of the partition, and this is the second. So you say this is 0 and this is 1. And then you subdivide each of these cells, and then this becomes 0, 0, 0, 1, 1, 0, 1, 1. And this way I also know the exact address. Okay? Any questions about this? I have a couple minutes. So what is the use of this? Well, in a sense, in this case, it's not that perhaps useful because the map that we started with is already rather straightforward. But for instance, one thing I can do is, using the shift space, I can construct some bizarre periodic point and then translate it back to a periodic point for this. Because certainly, let me just write it here. So here's a periodic point for the shift map. And then keep repeating this, okay? This is my pattern. What you would say this is like my block code. Now this corresponds to a unique point here, okay? Now computing this exactly is going to be complicated here, and you're going to have a hard time drawing it. It is there, okay? So what does this mean? This means that this is a point that started here. Okay, let's try to identify where this should be. And you see, I need the inverse of phi existing as well, because I want to be able to go back as well. So where is this periodic point? This is the same picture. This is my diagonal. This is the midpoint. And that's my f. So how do I read this? So I want to think of this as the address of some point, just like we did in the beginning of this class. We started with this square root 2, and then we found the address. Now we're starting with the address, and I'm saying find the point that corresponds to it. Okay? So this is the 0. The first entry is 0, which means that the point, this periodic point that I wrote, starts here. It should be in here. It's not here. Then it's at 1, which means that divided by 2, it has to be here. Then divided by 2, it has to be here. Then 1 has to be here. Then divided by 2, it has to be here, and so on. Do you get the idea? Okay. And in terms of like storing information too, I'm not saying that this is going to be useful to be able to write this many sort of accuracies and stuff, but being able to do it is very good, is very important. And part of why you want to do something like this is because these systems are very chaotic. It depends very strongly what point you start with. You need sort of like very good precision to get what you want, which ultimately leads to saying something like this is also the starting point of being able to use simulations. Because ultimately simulations are all about approximations, and if your system is so that you cannot handle the errors, then whatever you're simulating actually has nothing to do with what you're actually trying to do. Even between math and simulations. Pure math and simulations. Okay? Any questions about these? So this is like a starting point of symbolic dynamics. Next week, I want to discuss some more examples, but next week we're going to sort of combine this with iterated function systems. Okay, thank you. Have a nice weekend.